Hi everyone, this is lecture 4 of the tutorial session for the NPTEL course, Introduction to Algebraic Geometry and Commutative Algebra. And, today is our fourth assignment solving class, and the topic is rings and modules with chains and conditions. So, I hope you are already familiar with the topics you learned in the class. So let us start with our first problem, that is let K be a field and let B, which is equals to Kx, where x is a variable, be a cyclic K algebra. That means the algebra generated by only one element, that is two elements, that is one from the field K and x, which is a variable. Then every K subalgebra A of B is a finite type K algebra, and finite type algebra means it's there should be a surjective morphism from uh, uh, like so every so finite type K algebra means I'm sure you are familiar with this, but if you are not, then so if A is a K subalgebra, that means if A is a finite type K algebra, then there should be a surjective map from kx1 to xn to A. That means it should be generated by finitely many elements as an algebra. Okay, so let's move on to the proof. Since B, that is Kx, is cyclic, that is generated by a single element x as K algebra, we have uh, B equals to Kx by Px for some polynomial P of capital X coming from K of capital X. So that means what we have done is that followed this map and took K of capital X to B, and you map your capital X to small x, and thus you get the map, and the kernel is a polynomial from the kernel is an ideal. So, and since K capital X is a PID, therefore the ideal is generated by a single polynomial, that is P capital X. Now let's move on to the methodology. Let's A be a K subalgebra of B, and we need to show that A is finally generated as a K algebra. Now, following the hint that was given in the your assignment, suppose f coming from capital A, with f is of the form summation of AIXI, where I is running from 0 to m, and where am is not equals to 0 for all of m greater than equals to 1. Now consider the tower of rings K of small f, that is coming from A, and that is coming from B. We'll show that B is a finite KF module. Now, since f equals to summation of AIXI x to the power I with m not equals to 0, we can express x to the power m in terms of lower powers of x and f. Now, how you can do that? You just simply take out am x to the power m here and write the negation term here, and then you take out your am to here, and you get this expression, and this shows that x to the power m belongs to this set, or you can say subset of kx. And by induction, for any n greater than equals to m, we can write x to the power n as a kth linear combination of 1 x square and up to x to the power m minus 1. Therefore you can write b as k of small x, and which is equals to of this form, and this shows that B is a finite KF module generated by this. Now, since B is finite Kf module and Kf is a finitely generated K algebra generated by F, it follows that B is a finitely generated K algebra. Now, since A is a subset of B and B is Noetherian, uh, that means that it is finitely generated algebra over a field, and you know that image of a Noetherian ring is image of a Noetherian module is Noetherian, and since this is Noetherian and this is surjective, so in this map A is the image of F, and therefore that is also Noetherian. Okay, so A is also finally generated as a K algebra. uh, so what they have said is that since A belongs to B and B is Noetherian, and A therefore any submodule of a Noetherian module is Noetherian, and therefore A is also finally generated as a K algebra. Now, since K belongs to A and A belongs to B, therefore B is a finite K module and A is also a finite K module, and you know that this is true as some module of a finite module over a Noetherian ring is Noetherian. Therefore, A is finally generated as a K module, and since Kf is finally generated as a K algebra, A is finally generated as a K algebra. So this proves that A is a finite K algebra. Now let's focus on the second problem that says that let B equals to K of n2, that is all two tuples where entries are coming from natural numbers, and yeah, with the monoid algebra over K of the additive monoid n2. And let x is your 1 comma 0 tuple and y equals to 0 comma 1 tuple, and then b which is of the from K of x comma capital Y, and the monoid monomials x to the power I y to the power j equals to eij, where your ij is coming from n2, form a base K basis of B, and let A be the K subalgebra of B generated by the monomials x to the power n plus 1 and y to the power n, where n is coming from your natural numbers. Then A is not a Noetherian ring, much less a finite type K algebra. Okay, so let us start solving this. Okay, so yeah, I mean, note that your B is the polynomial ring in two indeterminates x and y over small k, and the monomials x to the power I y to the power j for I comma j from n to form a K basis. Let A be the K subalgebra generated by x to the power n plus 1 and y to the power n. Your n is coming from natural numbers. Now we need to show that x to the power n plus 1 and y to the power n into y to the power n does not belong to the ideal uh, generated by x square y and x to the power n into y to the power n minus 1 for every n belongs to natural numbers. I mean, we need to show that So what is the definition of a Noetherian ring? That you know that so it should be a Noetherian module over itself. That means every submodule should be finally generated. In terms of ring language, you can say that every ideal is finally generated, but you get an infinite chain of kind of uh, ascending chain of ideals. So therefore you always get an ideal which is not finally generated, that we are going to construct. And so what we are trying to say is that let in be the ideal generated by x square y and up to x to the power n y to the power n minus 1. And suppose for contradiction that x to the power n plus 1 y to the power n uh, suppose for contradiction that x to the power n plus 1 and to the power n belongs to I to the and we will show that x to the power n plus 1 y to the power n does not belong to this ideal in, and therefore you will always get in plus 1 in plus 2 which will be containing the preceding term and and things. Now yeah, suppose for contradiction that x to the power n plus 1 into I to the power n belongs to in, then your x to the power n plus 1 to I to the power n equals to that it should be a not linear combination, it should be a combination of elements of x to the power I, y to the power I minus 1 and fi, where fi are coming from a, since in is generated by those. Now since a is contained in b, which is equals to k of x comma y, we can write each fi as a polynomial in x and y, and more specifically each fi is a k linear combination of monomials x to the power j plus 1 and y to the power j for various j greater than equals to 0, right? And the term fi dot x to the power I, y to the power I minus 1 contains monomial of this form, that is x to the power j plus 1 plus I and y to the power j plus I minus 1, where j is greater than equals to 0. Now for x to the power n plus 1 and y to the power n to be in the ideal, we need monomials on the right hand side to combine to get exactly x to the power n plus 1 y to the power n. Now if you consider the components and so then it now okay, let me do this clearly. If you consider the components like we need j plus 1 plus I equals to n plus 1 and j plus I minus 1 equals to n, which gives j equals to n minus I and j equals to n minus I plus 1, a contradiction, right? And more carefully, if x to the power n plus 1 into y to the power n equals to this summation of this form, then looking at the total degree in x and y, we have on the left side total degree equals to 2n plus 1, which is n plus 1 plus n, and on the right side each term is has degree at least 2i minus 1, so plus the degree of fi. And since fi are coming from a, the smallest monomial in a is x, which is of degree 1 obviously, and since fi has degree at least 2j plus 1 for some j greater than equals to 0, thus the degree of fi dot x to the power I, y to the power I minus 1 is at least it should be 2 into I plus j, which is coming from adding these two tuples these two numbers. And for the equation to hold, we need these two equations to be equal, but the left side is even while the right side is odd, so therefore it is a contradiction. Now there is another method also, like the monomials in a are of the form x to the power k1 plus dot 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 kr plus r, y to the power k1 plus dot dot kr, where ki is greater than equals to 0. Notice that for such a monomial, if we write it as x to the power a, y to the power b, then a minus b greater than equals to 1 always, I mean if you subtract a minus b, you should get this. And yeah, and if the monomial is a product of at least one generator. Now for x to the power n plus 1 y to the power n, we have n plus 1 minus 1 equals to minus n equals to 1. And if x to the power n plus 1 y to the power n is in the ideal generated by x square y into x to the power n y to the power n minus 1, then as an element of b equals to k of xy, it must be expressible as a combination involving only monomials x to the power a y to the power b with a minus b greater than equals to 2. But again, x to the power n plus 1 and y to the power n has a minus b equals to 1, and so it cannot be in the ideal. And if you now consider the ascending chain of ideals, that is ideal generated by x, which is strictly contained in ideal generated by x and x square y, and ideal generated by x square y and x cube y square, and so on. By step 1, you see that x to the power n plus 1 into y to the power n does not belongs to its preceding part for all n, so this is a strictly ascending chain, right? And therefore A is not a Noetherian ring, and since A is not Noetherian, it cannot be a finite type K algebra, as finite type K algebra over a field are Noetherian, right? As we have seen here and discussed earlier, that is this map. Okay, now let us focus on the next problem, that is that the set integer z uh, uh, rational polynomials such that f of z is contained in z, which is quite interesting, right? Because rational polynomials are also integer, no, like they you, you can put integers, as integers are rationals, so you can put integers in the variable, and therefore you can write it as f of z is contained in z, which is again a subset of q of x. So what they're saying is that this set int of z of integer valued polynomials is a subring of qx called the ring of integer valued polynomials, and for each prime number p and is k of fp, the subset m suffix p k bar equals to f of this integer valued polynomials, such that its vp of fk is greater than 1, that is the degree of like the multiplicity of the 0 there, it should be greater than equals to 1, which is again a maximal ideal in z. So what they are saying is that this subset mpk bar, this subset consisting of all a coming from in z, such that this condition should be satisfied. uh, it is a maximal ideal with residue field isomorphic to the prime field fp. This is actually important when you learn discrete valuation ring. I hope you will learn some time, or if you are already familiar with, you already know what I'm talking about, because the the polynomials which are zero at a point are forming the maximal ideals, which is actually the core construction from algebraic geometry. uh, okay, so let us go into the proof. Clearly, if f and g are coming from in z, then for all n coming from z, you can write it as this, right? A plus g of n equals to fn plus gn. F dot g of n should be fn of gn, and minus f of n should be minus of fn. So yeah, and all of these are contained in z, so therefore it is clear that in z is a subring of qx, and also it contains 1. Now for k bar of fp, choose a representative k of z. That means you can take an element from its residue class. Yeah, that is k mod k congruent to k bar mod p, and define your mpk as mentioned above, where vp is the periodic valuation. Now this is well defined. If k mod I mean if k dot equals to k of mod p, then k dot k dash equals to k plus pm for some m of z, and for f of int z, fk dash minus fk equals to f of k plus pm minus fk. And by Taylor expansion, f of k plus pm should be uh, f of k plus pm of f prime k plus pm, I mean combination up to two elements, two numbers, f double prime k plus so on. Since uh, f belongs to int z and all these terms are in pz, therefore fk dash congruent to fk mod p. Thus uh, I mean what I just said, thus vp of fk greater than equals to 1 if and only if vp of fk prime greater than equals to 1. So what I said earlier, that Vp is the multiplicity of the root at P, is not right, and I forgot actually. This is the p-adic valuation, and what is a p-adic valuation? That is one second. So the p-adic valuation is the highest number. So write it as, I actually forgot what is a p-adic valuation. So Vp of n is the, if I can write p to the power k into n1, that means such that n1 such that p does not divide n1, then Vp of n is k. So highest power of the prime p which divides n. So it is clear from that uh, I mean if this happens, then this happens, right? Because they are equal mod p means the pth power is exhausted in both of the values. Therefore this is true, right? Okay, I mean if it is greater than equals to 1, then uh, fk prime can be written as something like this: p to the power k1 of fk prime. And if not fk prime, suppose f star k prime, such that p does not divide f star k prime, and if you divide it by p, now since pk1 is there, so p should divide that, so therefore this expression also should be divided by p, therefore the p-adic values should be non-zero. Okay, now clearly 0 belongs to this set mp k prime k bar. Now if now we have to show that it is a maximal ideal. So if f and g belongs to m pk bar, then vp of p fk greater than equals to 1, and vp of gk greater than equals to 1. So vp of f plus g of k equals to vp of fk plus gk, which is less than equals to minimum of both of them, which is greater than equals to 1. Therefore it is, so it is closed under addition. And if f belongs to m of pk and g belongs to integer of z, therefore vp of then vp of fg of k, it should be vp of fk into vp of gk, which is again their sum. So it turns multiplication into addition, but it is clear, right? Because if you are given two integers n1 and n2, and one has something like this p to the power k1 of m1, and it has p to the power k2 of m2, and now if you multiply them, it should be p to the power k1 plus k2 of m1 m2. Therefore this k1 plus k2 is this, and k1 k2 is this. So yeah, it is clear. Now thus f dot g belongs to this set, and therefore m of pk bar is an ideal of int z. And consider the map. Now if we consider the map phi from int z of to fp, and which maps f to fk bar, k upper bar, which belongs to z mod pz, which is fp. This is well defined since yeah, you know, we have done this. And and we need to show that phi is a ring homomorphism, but this is clear again since phi of f plus g is f plus g k mod, and f k mod plus g k mod equals to phi of f equals to phi of g. And phi of fg equals to fg of k mod, and which is again fk gk mod, and which is phi of 5g. Therefore it is a ring homomorphism, which is a easy check, you can check it yourself. And now the kernel of phi is f of int z such that fk congruent to 0 mod p, and yeah, so therefore it is clear that this vp of fk should be greater than equals to 1, since p divides fk. And now we show that phi is surjective. I mean, for any a bar of fp, the constant polynomial is there. Therefore you can say that it is surjective also. And so therefore the first by the first isomorphism theorem, int z by kernel is isomorphic to fp, but you show that kernel is mpk bar, and therefore since fp is a field, it is a maximal ideal, because you know that for for commutative rings with unity, uh, if you sub it out by maximal ideal, it should be a field. Okay, now we focus on to our next problem, but before that we will take a 5-minute break, and then again we'll start. You can read the statement by yourself. Okay, so let us do the problem 3, 4.3. Let Pi be the sequence of prime ideals with Pi is not contained in Pj for I j coming from n with I strictly less than j. So what is we are saying that if uh, like P1 is not contained in 2, P2 is not contained in P3, something like this is happening, but others can happen and there is nothing said about it, like, oh god, so this can happen maybe. Okay, and you put a n equals to intersection of all the pi's where I is less than equals to n. So a1 should be p1, a2 should be p1 intersection p2, like this. Then an forms a strict descending chain of ideals in a, like a1 is p1, then p1 intersection p2 is contained in this a2, and like this it goes on, and this goes on. And deduce that if a is Artinian, that means all the descending chain of ideals is finite, then spec of a equals to spec max a, that is the set of all prime ideals equals to the set of all maximal ideals, and nil radical, that is nil a, that is all the nilpotent elements of a, that means all the elements whose certain powers are 0, is the Jacobson radical of A, that is the intersection of all the maximal ideals, and A mod MA, that is the Jacobson radical, is finite product of fields. Now we use a key lemma. It is standard in all the textbooks, specifically in first chapter of Atia McDonald, I think, or third chapter. But yeah, so what it says is that if a1 dot 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 an are ideals in the ring A, and if P is a prime ideal in A, such that it's in the intersection of all the ideals is contained in P, then sum of AI has to be contained in the prime ideal. In particular, if P is like equal, P equals to the intersection of all the ideals, then P has to be one of them. Okay, now we now come to the proof of the theorem. That is part 1, that is the set of all maximal ideals is the set of all prime ideals, and yeah, so by definition an is uh, are all these intersection of prime ideals such that I is less than equals to n, and an plus 1 is again a intersection of all pi such that I is less than equals to n plus 1. This implies this is an intersection pn plus 1, right? And therefore an plus 1 is contained in an for all n. Thus this says that the strict descending chain. Now to show strictness, suppose an plus 1 equals to an for some n. I mean, you can clearly see it by yourself, but again then if an plus 1 equals to n for some n, then an equals to an intersection pn plus 1. This implies an is contained in pn plus 1, but an equals to intersection of all pi I less than equals to n. So by lemma, sum of the pj has to be contained in pn plus 1, j is less than equals to n, so therefore it should be less than plus 1, but in the condition we have said earlier that pi is not contained in pj whenever I is strictly less than j. Therefore, uh, pj cannot be in pn plus 1, and therefore this equality is a contradiction. So yeah, now what you have gotten is that an is a strict descending chain. Now since a is Artinian, it satisfies the descending chain condition, which is every descending chain of ideals stabilizes. But if there exists an infinite sequence of prime ideals with this condition being satisfied, then an is a strict descending chain, right? Contradicting the DCC, that is descending chain condition. Therefore, no such infinite sequence can exist in an Artinian ring, and this means that any anti-chain set of pairwise incomparable elements in spec A is finite. That means if you take these kind of things, so combined with the fact that descending chains in spec A are also finite, we conclude that spec A is finite. And if spec A is finite, uh, uh, we have is that uh, it should be equal to spec max A, and it is a theorem that in for Artinian ring, uh, if spec A is your finite, and therefore uh, 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 it should be a maximal ring also. And also it is true for Artinian ring is that every prime ideal is maximal. So which I forgot to mention. So therefore this is why Artinian rings are important, also they are also rare. Okay, so now the next one is quite trivial, since we have already said that spec A equals to spec max A. You know that nil radical is intersection of all prime ideals, and the Jacobson radical is intersection of all maximal ideals, which we have done exactly here. That uh, I mean, okay, let us prove that spec A equals to spec max A. Then we can say that the nil radical is this one liner thing. Okay, let P be a prime ideal of A, and then A mod P is an integral domain, and since A is Artinian, A mod P is also Artinian, and Artinian integral domain is a field. It is a standard theorem. I mean, if A not equals to 0 in A mod P, consider the descending chain. By descending chain, a to the power n should be equals to a to the power n plus 1 for some n. Then a to the power n equals to a to the power n plus 1 of b for some b. And since AP is an integral domain, a to the power n not equals to 0. Therefore, 1 equals to AB, and therefore A is a unit. So it is always true that an Artinian integral domain is a field, and therefore yeah, A mod P is a field, and since P is prime, A mod P is a field, therefore P is maximal, and so you can use here that spec A equals to spec max A, and from this happens. Okay, so now we go to our last problem, that is A mod MA is a finite product of fields. I mean, let M1 to MR be the maximal ideals of A, then MA is intersection of all the MIs, and by the Chinese remainder theorem, you know that if the ideals MI are pairwise co-maximal, that is MI plus MJ equals to A for I not equals to J, then you can write it like this, right? And since each MI is maximal, each A mod MI is a field, and to show that the maximal ideals are pairwise co-maximal, uh, like uh, the sum, if they are not equal to A, uh, Then since sum of two ideals is an ideal, so it would contain in another maximal ideal. This would imply that both of the maximal ideals are contained in mk, and since all are maximal, this would imply that all of them are equal, contradicting I not equals to j. So yeah, we have proved that all the maximal ideals are co-maximal, or you can say I don't know. Okay, so therefore this is true that A mod MA is the product of fields. Okay, now let us focus on the problem 4.4. So you can again try it for 5 minutes and then we will start. Okay, so let us focus on the problem number 4.4. Let A be a commutative ring and V be a finite A module. We have to show that every surjective endomorphism F from V to V is bijective. Surjective you know already, and endomorphism means a morphism from an object to itself. And let F be a surjective morphism and A module homomorphism and set K equals to kernel of F. Then we have a short exact sequence. You know that we have already mentioned what is a short exact sequence in the class. 0 K V to V and 0, and let M of A be a maximal ideal. Tensoring the above sequence with A mod M yields an exact sequence K mod MK V mod MV to V mod MV, which is induced from A. And since B is finally generated over A, the A mod M vector space V mod MV is finite dimensional, and the map A bar is surjective linear endomorphism of this finite dimensional vector space. Hence, it is bijective, right? You know that a surjective linear transformation between two same dimensional vector spaces is bijective. Therefore, A bar is bijective. Therefore, K mod NK is 0. And as K is finally generated, Nakayama's lemma implies that K equals to 0, right? And thus F is injective, and since F is also surjective, it is bijective. Now, for the second part, it says that let U be an okay, so let U be a non-zero sum module of V. If V is Noetherian or V is finite, then V and V mod U are not isomorphic as A modules. So assume for contradiction that there exists an A module isomorphism from V to V mod U. Let pi V to V mod U be the canonical projection and define F as phi inverse mod pi from V to V. So the map is V to V mod U and to V. This is phi inverse, this is pi. So we have a map here, phi inverse pi. Then F is a surjective endomorphism of V, right? Because this is isomorphism and pi is surjective. Therefore, this any element here has a preimage here and any element here has a preimage here. So therefore, it is surjective. And moreover, kernel of F, which equals to kernel of pi, right? Because this is because phi inverse is an isomorphism, is non-zero. So F is not injective, and uh, this is because car of F equals to U. And if V is Noetherian, every surjective endomorphism of V is injective. This contradicts to this statement that, and if V is finite, every surjective endomorphism of V is bijective. Again, a contradiction. In either case, sorry. In either case, no such isomorphism phi can exist. Therefore, V is not isomorphic to V mod U. Now, for the last problem, let W be an arbitrary A module. If V is isomorphic to V DXM W as A modules, then W equals to 0. Assume that there exists an A module from V to V DXM W. Let pi is mapped from V DXM W to V be the projection onto the first factor, and define F as V to V. That means this pi and the something like this. So therefore there is a map V to V. Okay. Then V is surjective A module endomorphism of V, which is again clear from the map itself, and the kernel is 0 direction W because uh, uh, yeah, since pi is a projection map, and hence kernel of f equals to phi inverse of 0 direction W. In particular, kernel of f equals to W, and since f is a finite A module, every surject of surjective endomorphism of V is injective. Therefore, kernel of f equals to 0, and hence W is 0. And this could be a nice exercise. Okay, now we come into problem 4.6, and let A be a commutative ring, let V be a finite A module, and W a Noetherian A module. Then we have to show that and in the bracket respectively Artinian, and then we have to show that this homomorphism ring is Noetherian, and if you consider W as Artinian, then it is Artinian. Now, since V is finally generated, there exists an surjective homomorphism from A to the power n to V. You just take all the generators from V and take the cardinality and as n, and map all the EIs to those elements, and you get a surjective map. And applying the left exact functor home dash W yields an injective map, because again this is from commutative algebra, and if you are not familiar, I suggest you to go with those things, that why home dash W is a exact functor, left exact functor. That means um, first of all you need to know that if it is um, like covariant and or contravariant, it is contravariant. That means it changes the direction of the exact sequence, and therefore it uh, takes the surjectivity of the exact sequence to the injectivity of the exact sequence, but do not take the injectivity of the first exact sequence to the surjectivity of the second exact sequence. But anyway, you need to go through this, and applying the left exact functor yields an injective map, and using hom a to the power n W is isomorphic to Wn, W to the power n, we see that hom a Vw is a submodule of Wn, and if W is Noetherian or Artinian, then W a to the power n is also Noetherian or Artinian, and hence so is hom of Vw. Now let us move on to the last problem of the day, that is, let V be an A module, and if V is Noetherian, then uh, endomorphism ring of V is Noetherian, also respectively finite and Artinian if V is finite and Artinian, and in particular every A subalgebra of endomorphism ring of V over A is Noetherian, respectively finite and Artinian. Note that endomorphism ring of V, which equals to hom of V comma V, if V is Noetherian, then it is finally generated, and applying A with W equals to V, so that endomorphism of ring of V is Noetherian. And if V is finite and Artinian, the same argument shows that endomorphism ring of V is finite and Artinian. Any A subalgebra of endomorphism ring of V is an A submodule, hence it inherits the same finiteness property. I mean, this should be an exercise. Check. Okay, so this was our today's exercises mentioned in the form in the assignment. So if you have any doubt, you can mail me as always, and yeah, let us finish this today. Let's not to drag the length of the class. Okay, thank you.